Hi everybody! This integral seems to be giving some of your classmates some trouble, so let me go through this with you all. So we want to evaluate the indefinite integral, and that is the integral of x squared divided by the quantity of x squared plus 25 all squared dx. And what's our first step? Well, our first step, of course, is to look to see if we can do a u substitution. But very quickly, you'll see that you cannot let u be x squared plus 25 because then your derivative is 2x, and that's not really going to help. So we're going to use our trigonometric substitution to do this integral. So we're looking at x squared plus 25, that pattern, and when we have something squared plus something squared, do you remember? That's when we use our tangent substitution. In other words, we are going to let x equal a tan theta, but for our purposes, a is simply 5 because 5 squared is 25. So we're going to let x equal 5 tan theta, and I'll just put underneath that this is the pattern x squared plus a squared, where a is 5. Now, the problem doesn't have a square root in it, and we're used to seeing a square root, but that's okay. We can still use this substitution. All right, after we get x, our second step is to find the derivative. So let's take dx, and the derivative then is going to be 5, and the derivative of tangent is secant squared theta, d theta. Now remember, a lot of students forget that part. Don't forget that part. And now we want to make those substitutions back into our integral, one at a time. So starting at the top, we have x squared. So we're going to replace x squared with 5 tan theta squared. Real simple, right? And on the bottom, again, x squared plus 25. So we're simply going to put 5 tan theta in for x plus 25 to the second. Now, don't forget dx. dx has to get replaced, and it's going to get replaced with 5 secant squared theta d theta. And so now we've converted from an integral involving the variable x into an integral involving the variable theta. Now, why do we do that? What's our advantage? Well, because of the way this Pythagorean relationship works out, lots of things are going to start canceling when we use our identities. All right, so let's see what we've got. On the top, if I put it all together, let me just put it all together on the top to make it nicer. I've got a 5 squared and another 5. And so if I put that together, it looks to me like I have 125 as my coefficient. Again, that's the 5 squared and then the 5. I also have a tangent squared sitting on top and a secant squared. Now, what about that bottom? Well, if I want to simplify it out, 5 squared is 20. So 5 squared is simply going to be 25. And tangent squared, well, that's tangent squared. And so on the bottom, I have 25 tan squared plus 25 all squared. And that's good. Remember, we're looking for patterns here. And so we like to set it up so we can factor. So we are going to take out, right? That's the whole trick with this trigonometric substitution. We're going to take out that common factor of 25 on the bottom. And so rewriting on the top, 125 tan squared theta, secant squared theta, bringing it all along. And in the denominator, I'm factoring out this 25, and it's leaving me with tan squared theta plus 1. But all of this, right, is being squared. All right. So far, so good. Now, what's our little trick? What are we doing? We are using our Pythagorean identities for trigonometry to simplify down. And tan squared plus 1, that's just secant squared, right? That's just secant squared. So really, I'm going to put one more step in here just so we can lay it all out. Some of you guys might jump right away and say, I see everything that cancels, and that's great. I'm just going to put one more in here to make sure I don't lose anything and don't make any silly little mistakes. But in the numerator, again, I've got 125 tangent squared secant squared. And in the denominator, notice I have 25 squared and secant squared squared, which is secant to the fourth. All right, so now I'm going to lay out and cancel some things. So what do we have on top? Let's see. I have, oh my goodness, so I've got big things to cancel here. Let me move up a little bit on my integral here. And we've got a bunch of 5s. In fact, I'm just going to pull out 125 is actually 5 cubed, or I'm going to actually factor it out just because I'm going to do some cancellations in my head, and it works way better if I do this. So I hope this is okay with you. I took 125 and I'm pulling it out because it's my coefficient, and I rewrote it as 25 times 5. And on the bottom, 25 squared is 25 times 25. And the reason I did that was so that I could visually see that I cancel my 25s. And 5 goes into 25 5 times. So I did that for my purposes, but you can use a calculator or you can cancel that however you want. But I'm winding up with a coefficient of 1/5. Now I'm also going to make another cancellation here. I notice I have a secant squared, and that can cancel with the secant to the fourth, and that's going to leave me with a secant squared on the bottom. And so let me put this all together. That means I'm going to have a tangent squared on top and a secant squared on the bottom. Notice I pulled my constants out front, or my coefficients out front. And so let me make this a little nicer. That's 1/5 tangent squared over secant squared. Now, we might be thinking U substitution here. But why does U substitution not work? It's because the secant squared is in the denominator, right? We need the secant squared to be in the numerator in order to do a U sub. So how about, well, there's really not much we can do as far as integration. And generally when I get to this point and I get stuck, this is when I use my identities of tangent and secant and convert everything in terms of sines and cosines. I like to convert things into sines and cosines because I can manipulate them a little easier than tangents and secants. And besides, again, I can't use a U substitution because the derivative, secant squared, is in the denominator, and that's not good. So instead, I'm going to convert these tangents and secants into sines and cosines. So what I have going on, and let me rewrite this, is I have tangent squared theta, and then I have a 1 over secant squared theta, and I'm writing it like that because my next step is going to be to convert into sines and cosines. All right, so now I'm setting myself up, and here we go. So we have one more level here. Let's see. So in the bottom, I have 1/5 times the integral of tangent squared theta. And tangent squared theta can get converted into sine squared over cosine squared. That's really nice. Why is that really nice? Do you guys see what I see? Do you see what's going on here? Secant squared, well, what's about 1 over secant squared? Isn't that the reciprocal of cosine squared? 1 over secant squared is just cosine squared, because cosine is 1 or secant is 1 over cosine, right? So cosine squared is the same thing as 1 over secant squared. That's our identity. They're multiplicative inverses of each other, right? And why is that beautiful? Well, that's beautiful because cosine squared cancels out. So what's that leaving us? So that's leaving us with 1/5 times the integral of sine squared theta d theta. Whew! All right. So minutes later, After the start, we have reduced our original integral into something really simple, 1/5 sine squared theta. Now let's work that out. So let me turn to a new page to do that. So here we are, and I've written down both the integral 1/5 sine squared d theta, which is what we're working on, and I also copied on to it the substitution that we had originally made at the beginning, which is x equals 5 tan theta. Now I'm going to need that. If you know where we're heading. After we take this integral, we're going to need to go back and substitute back for x. So I copied that down so I have that. Now let's take the integral of 1/5 sine squared theta d theta. Ideas? Do you remember from our last section when we talked about even powers of sines and cosines? Remember we said that in order to evaluate or integrate an even power of sine or cosine, we had to use those power-reducing formulas. Do you remember? We're going to need our power-reducing formula, so I'll just jot that down. We need our power-reducing formula, and you remember what that was? Of course you do, right? That's the 1/2 thing. All right, so here we go. Ready? Sine squared with the power-reducing formula will be rewritten as 1/2 times 1 minus cosine 2 theta d theta. Remember our power-reducing formula. Yeah, that's what that is, right? 1/2 times 1 minus the cosine of 2 theta d theta. And now we're going to integrate each of those pieces. I'm going to pull out my half. So in front, I've got 1/10. That way I have 1/10 in front. And I'm going to have 1 minus the cosine of 2 theta. And why is the power reducing formula so good? It's so good because it removes that power. And now I can just integrate my single cosine, right? I can just use the quick rule for integrating cosine, antiderivative of cosine. So we have in front 1/10. And now we can straight up take the antiderivative of 1, d theta, is going to be theta. And the antiderivative of negative cosine 2 theta is just going to be negative 1/2 sine 2 theta. Think about this. Antiderivative of cosine is sine because the derivative of sine is cosine. That negative has to stay in front, and because we have that extra 2 right there, remember it has to come out when we take the antiderivative by flipping over, right? So the antiderivative of negative cos 2 theta is just negative 1/2 sine 2 theta plus c. And now we have to go back and replace for x. But here's a little thing that we haven't talked about in class, but it's so important. When we go to draw this triangle, so let's draw this triangle. Let me draw this triangle because we know this is the last step, and this is probably our favorite part, right? We're converting from theta into x's. So we draw ourselves a little right triangle, and we take the relationship that x equals 5 tan theta, and we rewrite it, right, by dividing both sides by 5. Well, this is what I do, as x over 5 equals tangent theta, and that helps me to label my triangle, right? Because tangent is opposite over adjacent, and so I'm going to label the side opposite theta as x, adjacent theta as 5, and then using good old Pythagorean theorem, that's going to tell me the other side is simply the square root of x squared plus 25. Those are those Pythagorean relationships. Now, if I go and try to find the sine of 2 theta, well, now I'm in trouble because what's happening is I have just the angle theta. And so in order to use this beautiful right triangle that we know and understand, I have to do one more conversion. So I'm going to do one more conversion for us, and that's this. I'm going to rewrite the theta, but instead of writing sine 2 theta, because this is a double angle, I am going to use the double angle formula to rewrite sine 2 theta. That is, sine 2 theta by the double angle formula, if you look up and remember, is 2 sine theta cosine theta. The double angle formula takes a double angle and converts it back into single angles, and that's what I need from my triangle. I need just a single theta, not double theta, but I need a single theta. So that's what we're going to use right there, that formula and that triangle, to finish up our problem and make our conversions from thetas into x's. We are so close to being done, and this one is such a long problem, but we're just going step by step, and it's understandable, right? It's not too bad. All right, here we go. So we're going to replace theta with something involving x. Well, this is where I'm going to say, well, what is theta? Theta is the angle whose tangent is x over 5. I'm just going to put a little note here, right? Tangent of theta equals x over 5. So that means the arctangent of x over 5 is theta, or theta is the angle whose tangent is x over 5. And so we can rewrite theta as the arctangent, or the inverse tangent of x over 5. So theta is just the arctan, or inverse tan, of x over 5. How about the rest? Well, let me do a little cancellation here, right? So now what I have is minus, and now I have to put in sine of theta. So now we're working on sine of theta. The sine is, let's think it through, the sine is opposite over hypotenuse. So hopefully you're putting in place of sine x over the square root of x squared plus 25. And in place of cosine, what are you putting in? That you're putting adjacent over hypotenuse. So we should be putting 5 over the square root of x squared plus 25. All plus c, right? All plus c. And I think I'll multiply those together. Let's see what we get. So I'm getting 1/10 times the inverse tangent, or if you like, arctangent of x over 5, minus, on top I have 5x, over the square root times the square root just gives us x squared plus 25, parentheses closed, plus c. Well, I would laugh and say, have fun putting this into web work with all those extra parentheses, right? But that would be the answer that we finally have when we've converted from thetas back into x's. And that is the antiderivative of x squared over x squared plus 25 quantity squared dx. It is beautiful mathematics when everything comes together like that. So what was our keys? Our keys here on this page, after we've done our main substitutions, our keys are, once we get sine squared, remembering we have to use a power reducing formula to integrate it. And then at the end, we can't convert from x's back into a double angle, or a double angle back into x's. So we have to use our formula that sine 2 theta is 2 sine theta cosine theta in order to go back and convert back into our x variable. Alrighty, guys. Good luck as you work your own problems in WebWork, and if you have any questions at all, please don't hesitate to reach out.